Okay, I thought I needed a lecture on regressions since it might be difficult for some students. As a basis, I'm using PowerPoint prepared by Professor McCabe at Maximum Likelihood Estimation class. It was a class on advanced statistical models, but she did do an overview of linear regression. So there are a bunch of different levels of understanding statistics. First, how to interpret the results. You do something in SPSS or R, you get something like, what the hell I'm doing with this, right? So this is the very first level. Then the next level, you're making a decision whether to use a regression and what kind of regression. So for instance, if your dependent variable is interval ratio and has like lots of values. Remember, we have basically three main types of variables: nominal, ordinal, and interval ratio. So if your dependent variable is interval ratio and it has lots of values, you probably do a linear regression. If, for instance, your dependent variable is some kind of ordinal variable, for instance, like level of support, I strongly support something, I somewhat support something, I neither support nor like whatever, and I do not support something. So you have some kind of range of approval. For instance, in this case, you do ordered logistic regression. If, for instance, your dependent variable is some kind of bunch of events within a particular year, and you have a data set on a bunch of years, you do a survival model, etc., etc. So, but in this introductory class, we only touch upon linear regression. Another level is intuition, like how it works. And other two levels, like math behind regression and math behind math of regression, or people who understand this stuff, they usually go into PhD programs in statistics. I am not among those people. So what's the point of linear regression? This is how it looks in matrix form. If you have taken calculus in high school, you might remember it. But this equation is probably more familiar to you. So y is usually, not usually, always is your dependent variable, x is your independent variable, beta is your coefficient, and this last Greek thing is an error term. And how you interpret your coefficient, beta, the unit change, maybe write it down somewhere, probably the most important thing about regressions. The unit change in x produces a specific percentage of change in y, and that percentage is this beta coefficient. Let's see. Okay, now we need this slide. A bunch of high-end math, derivatives and stuff. I will not torture you with this. So assumptions of regression. If you have those assumptions, you are free to do a linear regression. First, linearity. If like relations between variables are linear, like one unit change in one in independent variable leads to exactly the same change in dependent variable, and those relationships are constant throughout the whole line. Another thing is exogeneity. What it means is that independent variable affects dependent variable. It's like a fancy word for a very simple concept. Another thing is multi-collinearity. It means that if you have a linear regression with a bunch of independent variables, those independent variables are not correlated among each other. If they're correlated among each other, it means that you probably have to drop one of the variables to avoid this multi-collinearity. And another assumption of linear regression is homoscedasticity. And what it means that errors are the same across like all values in your distribution. So they are not different in different parts of it. Okay, let's see next one. Next one is properties of linear regression. Let me try to show you this thing. First one is unbiased. Yeah, this is like a thing from Kennedy textbook on econometrics, and it has a very good graphic explanation of this stuff. So what you see a sampling distribution. And the idea is that if you take a bunch of samples from the same population, remember population is what we study, is the whole thing. And scholars usually don't study populations. They study some kind of a sample of population because of the usually data availability. So when you take a bunch of samples and you have a bunch of parameters, for instance, like mean of your particular variable, and if it's like similar, very close, it means that you have this unbiasedness quality. If, like in this case, you see that when you take a bunch of different samples from the same population, and for instance, mean is different, it means that you have a bias in your sampling distribution. Another thing, if I remember right, would be efficiency. Another nice graphic which explains this. Again, when you take a bunch of different samples from the same population, and when you have, for instance, one sample where variance is smaller, you probably need to take this particular sample and not the sample when you have wider variance. So this is the quality of efficiency. It means that distribution has a smaller variance. And another thing is, what's the next one? Another thing is consistency. If you have the same samples, you get kind of similar results. Okay, what's next one? 33. It's a bunch of R code. Student who knows R might take a look at this. I will post it in. Yeah, here it is. So what you do with regressions and how you decide whether or not you have a good model. You run a specific thing called goodness of fit and R square. For linear regressions, this goodness of fit is R square. And what R square tells you, it's usually somewhere, like if you are very lucky, you have like 0.3, 0.4. It means that, for instance, if it's 0.4, 40% of your variation in your dependent variable is explained by your independent variables. This is the meaning of R squared, the percent, which is explained by your independent variables. But there could be problems with R squared, and Professor McCabe gave a good example of this. So for instance, you have a bunch of regressions and they have the same R squared value, but situation is pretty different. So in first case, you see that error, pure error, it's kind of randomly distributed. In the second case, lack of fit, you see that your R squared, what you have in the data doesn't account for a linear relationship, and it's kind of lack of fit. Probably in this case, you should use some different model, maybe a logistical regression. And outlier thing is when you have some like extreme values, and also so your regression doesn't very well fit into the data. It means it doesn't very well explain change in your dependent variable. And the last one, for whatever reason, it's called influence. When you have like your distribution in two separate places, and you still have kind of the same R-square value, but your regression model does not very well explain what's going on in your data. Okay, next thing would be more things. When you look at your regression model, your model fit, you have to think about things like muted variable bias and collider bias. What it means, as like usual in regression, we think that your independent variable has some kind of effect on your dependent variable. But the problem is there could be some other variable, for instance, in this case, they call it W, which also has some kind of effect on both variables, your dependent variable and your independent variable. You could do a bunch of things with such situation. First, you might include this variable into your regression model. However, if this muted variable which you have included affects both x. Let me see. Yeah. If you think that there is a strong correlation between one of your independent variables and your muted variables, then you cannot include this muted variable in your regression, because you will have a thing called, remember, multi-collinearity, when two variables which are included in the list of your independent variables have a high correlation coefficient. And collider bias is a situation in which your variables in your already existing model, for instance, your independent variable and your dependent variable, they both have some kind of effect on your muted variable, W variable. So in this case, you have collider bias and you don't do this. So it looks very like general. Let's have a look at the example. A very simple one. Experience and income, two variables which probably have some kind of correlation, right? And also you think there might be muted variables, for instance, gender. For instance, we all know that in the United States, women make less than men. So controlling for gender in this case makes perfect sense. But there is, for instance, such variable as a number of cars, right? A number of cars is a variable which affected by income, right? So there is a high correlation between those two variables. Remember the situation about which we talked like a few seconds ago. So when you are thinking about this particular situation, this problem, you probably will not include a number of cars in your model. Let's see. Yeah, that's what I wanted to talk to you about.